Welcome to our ClimTip webinar series. ClimTip is a European-funded project on uncertainty-aware quantification of climate tipping points. And we have this webinar series to talk about all various aspects of tipping point science from different disciplines. And today we have Levke Caesar from Potsdam Institute for Climate Impact Research, PIC, to connect the dots and make these links between tipping points and planetary boundaries framework. To quickly introduce, Dr. Levke Caesar is a climate scientist. She specializes in Earth system dynamics and planetary boundary science, and her work focuses on understanding the impacts of human activities on global systems, with an emphasis on ocean circulation, climate tipping points, and sustainability. Dr. Caesar is a co-leading the Planetary Boundaries science team at PIC, contributing to advancing the representation of Earth systems in global frameworks. And she combines expertise in data analysis, interdisciplinary collaboration, and science communication to drive impactful research and foster innovative solutions for global environmental challenges. With that, I'll give the word to Levke Caesar.
Thank you all actually for having me. So I'm going to give a presentation titled From Tipping Points to Planetary Boundaries, which is ironically also kind of describing my scientific career. As Kurt mentioned, I'm a physical oceanographer actually also, so I studied climate physics, but then did a lot of research on the Atlantic meridional overturning circulation, looking at the tipping behavior here, and now I am leading the Planetary Boundary Science Lab at PIC. So I'm already kind of changing the order from this title. So I'm not going to start with tipping points today, but with planetary boundaries and planetary health, because that will be the main focus of this presentation. I am going to talk about the links to tipping points, tipping elements, but want to first of all give you the solid foundation on, okay, what do we actually mean when we talk about planetary health? So let's start with the definition of planetary health, at least how we see it scientifically or define it scientifically. It's important to note that the current stable, or at least relatively stable when compared to the Earth history, state of our planet is not guaranteed. We are living in a time where the overall living conditions on Earth are quite reliable, meaning that internal processes can mainly mitigate external pressures, and most of the planet remains in a habitable state supporting life. And this is what we refer to as a healthy planet. But our understanding of the Earth system indicates that the factors that guarantee, or the factors that determine the stability, resilience, and habitability are not permanent or guaranteed. So let me illustrate this in more detail. When we talk about planetary stability, we refer to the Earth's capacity to maintain relatively constant conditions over extended periods of time. For example, the last 12,000 years of the Holocene. During that time, the global mean temperatures varied within just a 2 degrees Celsius range, resulting in relatively stable and predictable living conditions, which also enabled the rise of human civilization. But if we look further back in time, temperature variations of at least 5 degrees or even much more were common, depending on how much further we look back into time. When we talk about planetary resilience, we refer to the Earth's ability to withstand and recover from disturbances. For example, as a forest can recover after a wildfire. This capability of the planet becomes even more critical under human-induced pressures that we're seeing right now. For example, about 50% of the human-caused emissions of over 1 trillion metric tons of CO2 have been absorbed by the oceans and terrestrial ecosystems, therefore significantly buffering the rise in global temperatures, and this is basically what determines the resilience of our planet. When we talk about habitability, or basically life support functions, we refer to essential processes provided by the Earth system that sustain life. For example, we don't just have liquid water on Earth, which of course is a prerequisite for life, but we also benefit from a functioning freshwater cycle between soils, plants, and the atmosphere. Additionally, we have these stable temperature ranges that support life in many regions. And for example, we have also an ozone layer that protects us from harmful UV radiation. So all this together is what we call planetary health. Now, from an Earth perspective, some might say that a planet can neither be healthy or sick. And I actually have been getting these comments from time to time. But it's important that if we define planetary health as I just did, then of course we can say that the planet can either be healthy or sick. And we can also link planetary health to basically our ability of humans to thrive on this planet. And this is kind of illustrated here in this figure, which shows the co-evolution of the total human population in the lower panel compared to the evolution of the global mean temperature in the upper panel. So humans have been around for a few million years, humans in general, but when we talk about the modern human, that is Homo sapiens, that has been around for only a few 100,000 years. As climate or a system scientists, we know that this means they evolved during the ice ages, meaning that through most of this time span, living conditions on Earth fluctuated quite a lot, as you can see by the temperature fluctuations here of several degrees in the global mean. At this point in time, the total number of humans on Earth is believed to be 10 million people or less. And it's only with the beginning of the Holocene, about 12,000 years ago, that temperatures and therefore living conditions on our planet stabilized, whereupon mankind invented agriculture, was able to settle down, modern civilizations emerged, and rose in numbers. In the beginning, just a little bit, but of course, later exponentially. And it's around 1750, with the beginning of the Industrial Revolution and subsequent advancements in agriculture, medicine, and sanitation, that humanity's population began to grow really rapidly, from 1 billion in like 1804 to over 8 billion today, establishing ourselves basically by now as the main driver of planetary change. Now, it's important to know that the changes to the Earth system that are caused by humans are nowadays so great that a lot of people refer to this time, or a lot of scientists refer to this time as the Anthropocene, meaning the age determined by humans. This becomes, or why we call it the Anthropocene, becomes particularly evident when we examine how key socioeconomic trends that you can see on the left-hand side correlate with those of the Earth system. So all these time series start in 1750, which, as I just mentioned, marks the beginning of the first industrialization in Great Britain, with inventions, for example, of the steam engine or the mechanical loom. And while this period also initiated the previously mentioned phenomena such as urbanization or the growth of global population, the most dramatic increases are observed around 1950, which is highlighted in all these time series in red. This applies, for example, for the use of energy, water, and fertilizer consumption. And these extreme use of resources has had direct impacts on the Earth system, which you can see on the right-hand side. So most of you are probably familiar with the rise in greenhouse gases in the atmosphere, like CO2, but also methane and so on. But we can also see a significant increase in ocean acidification, loss of rainforest, an expansion of cultivated land, and overfishing in the oceans. And with this beginning, like whether or not officially the beginning of the Anthropocene is a different topic in a scientific discussion, but let's just call it that. With this beginning of this human-driven time, a new question arises, and which is, what are the non-negotiably planetary preconditions that humanity needs to respect in order to avoid the risk of catastrophic environmental change at continental or even global scale? And this is what the planetary boundary framework tries to answer, to define. That is the safe limits for key Earth system processes. And these boundaries are based on the understanding that crossing certain thresholds can trigger nonlinear, potentially irreversible changes that move the planet away from the stable conditions of the Holocene. So a conceptual description is shown here. You can see in the left panel of the figure that some processes, like for example the melting of the Arctic sea ice, are governed by tipping thresholds. This is then what we call a tipping element, and the threshold is the tipping point. So these are points beyond which feedback mechanisms, like for example in this case the ice albedo effect, cause abrupt changes that you can see here. These thresholds are inherent property of the Earth system, and we typically identify them along one or more control variables. In this case, for example, the CO2 concentration on the atmosphere, or we could also plot it with respect to the global mean temperature evolution, or so on. In contrast to that, other processes, like for example, land use change, so basically how we change the land of the planet, whether it's forests, grassland, cities, and so on, shown here on the right hand side, they do not have those clear global tipping points. But what we see is that or changes basically in them can lead to gradual degradation of ecological functions. In this case, it would be carbon storage or biodiversity. And while these changes might not trigger a global tipping point on their own, they can definitely weaken Earth system resilience and increase the risk of tipping cascades in other domains, like then, for example, climate, when we look at the uptake of land from carbon, or biosphere integrity. They can also trigger local or regional thresholds, like, for example, forest dieback or lake eutrophication, so dead zones in lakes, which then, when we aggregate them across regions, can also pose global risks. So in both cases, then we can define a planetary boundary, and you can see here, so it's not that ideally visible, that they are basically placed at the beginning of this zone of uncertainty that normally surrounds a threshold, meaning that we basically work on what we call the precautionary principle. So we put it at the beginning of the zone of uncertainty, and with that, we create a safe operating space where the risk of crossing critical boundaries remains hopefully fairly low, even though there are some uncertainties about the dynamics of the system. Now, given this definition, the scientists concluded already in 2009, which is when this framework was first introduced, that there are 9 processes/systems that are key in determining planetary health. And yeah, I always worry that this is a little bit boring, but the processes are key critical, so I'm just going to go through them. It's on the one hand side climate change, probably not really surprising. So the process of changing the radiative balance of the Earth, for example, by accumulating greenhouse gases in the atmosphere, which then affects global temperatures and climate patterns. It's the change in biosphere integrity, that is the decline in diversity and or extent and health of living organisms and ecosystems, which can then affect the planet's ability to support life. It's the already mentioned change in land system, or how we use our lands. That is the transformation of intact nature due to, for example, deforestation or urban spread, which can erode ecological functions such as carbon sequestration. Then it's freshwater change, that is the alteration of freshwater cycles, including rivers, soil moisture, which can then add up to impacts on the functioning of nature, again, such as carbon sequestration and biodiversity, and cause shifts in future precipitation levels. So you can already see here a lot of these further boundary processes link back to what we sometimes also call the core planetary boundary processes, which is climate change and the change in biosphere integrity.
Because I'm already in the call,
Hi, Paul. Maybe you can mute yourself. Then the 5th one is the modification of biogeochemical flows. That is the disruption of natural cycles of essential nutrients, mainly nitrogen and phosphorus, that affect soil health and water quality. It's ocean acidification, that is the alteration in ocean conditions, in this case, ocean acidification, which impacts marine biodiversity, and also the climate regulation capacity of the ocean, so that is the ocean's ability to take up carbon. It's the increase in atmospheric aerosol loading, so air pollution basically. So that means it's the rise in tiny particles in the air from either human activities, but also natural sources, which affect climate by altering temperature and precipitation patterns, mainly via the radiative budget. It's the depletion of stratospheric ozone, that is the thinning of the ozone layer in the upper atmosphere, which is or has been primarily caused by human-made chemicals, which, if it's thin, basically can increase the harmful UV radiation that reaches Earth's surface. And last one, and I know this title is a little bit strange, it's what we call the overloading with novel entities. So what we mean is the introduction and accumulation of human-made substances, such as plastic, chemicals, and so on, into the environment. which can disrupt the other 8 planetary boundaries and also accumulate in the biosphere, which can increase the risk of permanent damage to life. Now, I know, long list. These colors already indicate the status of the different boundary processes, but I'm going to talk about that later more. When we compare these processes to the conceptual description I gave you before, we can see that some of these processes do have global thresholds by themselves, but others basically pose planetary risk in more complex, aggregated ways, as I've explained before. And basically, the division or categorization is that what you can see here in the upper panel, that is climate change, ocean acidification, and stratospheric ozone. These are the tipping prone or tipping type basically processes. So they have well-defined science-based thresholds at a global level. So for example, I mean, with climate change, we know that due to all the different tipping points that have been determined in the climate system, whether it's permafrost, ice albedo loss, and so on, we know that when we cross a certain CO2 level or temperature, we can see, or this can lead to abrupt and potentially irreversible Earth system shifts. It's similar in the ocean, that ocean acidification has a chemical tipping point, basically, beyond which marine ecosystems, especially calcifiers like corals and plankton, start to collapse. And with stratospheric ozone, we also see that basically there is this tipping point behavior that if, well, I guess coming from the classical tipping point definition as a climate scientist, we wouldn't necessarily call it tipping point behavior, but we do see that we have the global threshold under which basically we do not have a working stratospheric ozone layer. In the lower panel, then, you see the boundary processes that do not really have this clearly defined global threshold, but they are still important and impact the health of the Earth system because they can basically cause what we call cumulative degradation. So for instance, deforestation doesn't have a single global tipping point, but it can steadily reduce carbon sinks, disrupt rainfall patterns, and fragments ecosystem. Biodiversity loss also kind of happens more dispersed, but when enough species are lost across ecosystems, we can also see that, or it's possible that the underlying functionality of ecosystem breaks down, and this could make the entire Earth system more fragile. And then also some of these basically processes can trigger regional tipping points. For example, a collapse of forests into savanna, as it could happen in the Amazon rainforest, basically, if we see too much land use change. And then we have boundaries like aerosol loading or chemical pollution that also do not really have a global threshold, but due to complex interactions with the other boundaries could also destabilize key regional climate system and introduce irreversible novel risks. So I know the table isn't that great to look at, but the important take-home message is that not all of the planetary boundaries are really directly linked to tipping points or are about tipping points. So some are rather about resilience erosion or like pressure basically on the Earth system. But together, overall, they can form this safe operating space for humanity, and breaching any one of them could basically feed back or link to others and lead to an overall loss in resilience and stability. So I hope this already partly explains how planetary boundaries and tipping points are related, because I wasn't 100% sure basically on the audience, just to get everybody on the same page. There are multiple definitions of tipping points, but a fairly common one is basically saying that a tipping point is a critical threshold at which a small perturbation in external forcing can lead to a large, nonlinear, and often irreversible change in the state of a climate subsystem. And when we compare that to the planetary boundaries, basically side by side, we can say that, okay, planetary boundaries are not those critical thresholds, but are rather the science-based limits that define the safe operating space for humanity. So basically aiming at keeping key Earth system processes like climate, land, and freshwater in stable states. The purpose here is to prevent destabilization by staying well away from the thresholds. A tipping point doesn't really, I guess, have a purpose. It's more a description of basically where do we have a threshold that shows that destabilization occurs. The nature of change is also different. So basically, a lot of planetary boundaries could, but in principle, they could be based on tipping points, but a lot of them are actually way more gradual. While tipping points, of course, are per se, per nature, basically about nonlinear changes. The threshold, then basically the use of the threshold is also different. As I said, for a tipping point, basically it's the, in basically quotation marks, point of no return. So when we see this gradual or this nonlinear shift, and at least for a long time span, there's likely a point of no return. While for the planetary boundaries, there's this precautionary principle saying, okay, we also include a safety buffer to be sure that we are not looking at these catastrophic environmental changes. And yeah, then examples, of course, when we talk about tipping points, we've got the overturning circulation in the Atlantic, the melting of the big land ice sheets, the Amazon, and so on. And planetary boundaries, yes, include climate change, but also really freshwater cycles, nutrient cycles, and so on. And the relationship is tipping points kind of were there first, I guess, in terms of a scientific concept, and they're now used to inform basically the setting or determination of the thresholds in the planetary boundary framework. But I'm going to talk about that also a little bit more in a moment. And also important to note that not all of the planetary boundaries are clearly linked to tipping points. Okay, so I hope that's somewhat clear. I know it's a kind of complex framework. I want to now spend the rest of my presentation actually on giving you a few more details on the planetary boundaries framework, because that is what my team is researching at the moment, and also give you the current status of the planetary boundaries as we diagnose them in our planetary health check from last year, with a new one coming up this September. So for this diagnosis, basically, of planetary health, it's important to note that each of the 9 planetary boundary processes, and they're listed here again, is represented by 1 or 2 measurable indicators, which we call the control variables, that are listed basically down here, which is also why you have 13 rows here, because some of the planetary boundaries have 2 control variables. Roughly, you could say, if you use a human analogy, that the planetary boundary processes could be processes within the human body, like thermoregulation, blood circulation, or basically your water and electrolyte status. And these are then measured by the control variables, body temperature or blood pressure, or basically the nutrient values in your blood. So really like the indicators that you can measure. Now, for each of these control variables, a planetary boundary has been established. So as mentioned, basically the idea is that as long as you're below the planetary boundary, you are in a safe operating space where planetary health can be preserved. And here you can now see the assessment for the 9 planetary boundaries from last year. And what they show is that, and you can see it here, 6 out of those 9 planetary boundaries are transgressed, and all of them, and that is shown by the little arrows here, show trends of increasing pressure, so suggesting further boundary transgression in the near future. And it's only 3 out of the 9 planetary boundaries that are still within the safe operating space, which is the stratospheric ozone depletion, the atmospheric aerosol loading, and ocean acidification. But ocean acidification, as you can see here, is on the verge of transgression, and it also shows this positive pressure. So not really good news. I don't really have the time to go over all 9 planetary boundaries today, but I want to highlight a few of them, starting with the climate change boundary, because it's the one that is most closely linked to tipping points and elements. Here you can basically see the transgression of the 2 control variables, and here you can show the time series of the 2 control variables. We're using for climate change on the one hand side the atmospheric CO2 concentration, which, as many of you might know, is measured in parts per million. So the boundary is set at 350 ppm, and this is actually based on the risk of triggering large-scale tipping points like ice sheet collapse or permafrost thaw. And you can see that we passed the threshold already in the late 1980s. And CO2 levels have been rising ever since. Currently, we have averaged of about 420 ppm. On the right-hand side, we have the second controllable radiative forcing at the top of the atmosphere, which is also included to account for changes in the climate system that are not necessarily linked to CO2 concentrations, for example, changes in albedo. This is measured in watts per square meters, and the boundary is here 1 watt per square meter above the pre-industrial level, which is assumed to be close to 0. And again, we are now way over the boundary with values of about 2.6 watts per square meters. So together, these indicators show that we are well outside the safe operating space for climate, and we start, or actually have been starting to see the consequences of that all around us. This was basically just indicated by this image. Important to note is that these events that are shown here are basically not what led us to determine the threshold for climate change, because, as I said, that is based on tipping points. But it's something that we can now see that is also happening when we cross it. So on the one hand side, we have wildfires, which are charged by the higher temperatures and prolonged droughts. We see urban flooding, which is driven by intense rainfall and also longer rain periods and more extreme rain events. We have the problem that low-lying coastal areas and island basins are facing flooding events and sea level rise, of course. And then also we see way more deadly heat waves, or whether they're deadly or not, of course, depends on the region, but prolonged, of course, periods of very high temperatures. So as I said, these impacts weren't used to define the climate boundary, but they also show that unless we're staying in the safe operating space, we do see this, what we call symptoms of boundary transgression. A second planetary boundary that I want to talk about is, I guess, at least in the climate science space, often less visible, but it's, basically as critical, and that is the changes in biogeochemical flows, especially nitrogen and phosphorus use. These are two nutrients that are essential for food production, but their overuse is actually one of the main drivers of Earth system destabilization, especially through water pollution and ecosystem degradation. You can see here how the global average use of phosphorus and nitrogen changed from 1961 until 2013. We're at the moment looking for updated data. And basically on the left, you see the phosphorus use rate, which more than doubled over this period. Phosphorus is essential for plant growth, which is why we are using it as a fertilizer. But the problem is that its overuse, especially when it runs off into lakes and rivers, is a major driver of toxic algae and cyanobacteria blooms. And it also damages freshwater ecosystem and can even threaten drinking water supplies. Then on the right-hand side, we see that there's a similar trend for nitrogen. Nitrogen use has risen, probably even a little bit more dramatically, which is largely due to synthetic fertilizer application, which helps boost crop yields, but also comes at a cost, namely water pollution, but also the release of nitrous oxide, which is a potent greenhouse gas, and it can also lead to dead zones in the ocean. So basically creating zones where there's hardly any life. So the key takeaway here is that while these nutrients are vital for agriculture, the way we're using them right now is pushing us beyond the safe planetary boundary limits. So there's definitely some changes needed in the nutrient management to bring us back into the safe operating space. And this is just to basically shortly show you, okay, how does this look on a map? So what areas are really the ones that are most in the high risk zones, that are most transgressing the planetary boundaries. You see here the same color scale as before in the overview picture. So basically everything that is green is beyond the global threshold. In yellow, we have the high risk zone or the zone of uncertainty. And then in dark red to purple, the areas where we say, okay, the boundary has been transgressed by quite a lot. And when we look at the phosphorus transgression, we see that this is especially severe in parts of North and South America, but also Europe and Asia. So basically where we use a lot of fertilizers, and it's kind of similar, not as bad for nitrogen, where we see this is also mainly basically in Asia Europe, and yeah, a little bit North America. So these maps highlight that the problem is not just basically what we do in the global mean and how we use the fertilizers, but also really, okay, where do we use them? Do we have hotspots? And where do we basically have to turn our attention to most? Then the last boundary that I want to talk about in detail is the ocean acidification boundary. I already mentioned that we are basically on the verge of transgressing this. This boundary is very directly linked to the climate change boundary because it's a direct consequence of rising atmospheric CO2. I already mentioned it, that the ocean takes up a lot of the CO2 or the excess CO2 that the humans put into the atmosphere, namely about 25%. The other 25% is taken up by the land system. And what happens is when CO2 dissolves in seawater, it forms what we call carbonic acid, which lowers the ocean pH level and reduces the availability of carbonate ions, which on the other side are essential for marine organisms that build their shells and skeletons, like, for example, corals, mollusks, and plankton. And this graph shows the progression of ocean acidification. The control variable is the Aragonite saturation state, which is basically this critical factor for the health of corals and shell-forming organisms. And the green line presents the pre-industrial baseline of the Aragonite saturation state, which was approximately 3.34. And then the red line is the planetary boundary. And we have two different data sets, and this is actually already showing one of the difficulties that we have with this framework, that of course we are relying on good data sets for good diagnostics. And there are some uncertainties in this, but basically both of these data sets show that we are more and more going towards the transgression of the boundary. Important to note is that we actually have new research from last year and this year that indicates that this true pre-industrial level is probably even a little bit higher than previously estimated. So in this case it would be lower, which could indicate that the boundary will be transgressed sooner than we thought. So really, really soon. Again, showing this as a map. Here we are comparing the Aragonite saturation state from the early 1980s with the most recent 5 period that we have data for, which is 2018 to 2022. And the color indicates percentage change. Basically everything in red and orange, and that's basically everywhere, has experienced a drop in the saturation state. And what you can see here is that the areas that are most impacted are actually the Southern Ocean and the Arctic Ocean, mainly because the water temperature is that cold, and that makes them already more, or that means that the Aragonite saturation state is already potentially lower, and we therefore see the percentages, or the percentage change is bigger. And the problem that we have is that for some polar regions, the water is already now undersaturated, meaning that the water is no longer chemically favorable for organisms to build their shells. And you can basically see why this matters. It's really now dissolving the shells, which are normally forming the base of the marine food web. So ocean acidification as a process is really harmful to the whole ecological health of the Earth system. So also really showing ocean acidification is a global problem, but we also really have this regional hotspots of vulnerability in the polar region and need to slow this down. Even though one can say, okay, it's good that the ocean takes up extra carbon because it does, of course, reduce the warming in the atmosphere. Now, bringing this basically back to the tipping points. As I said, the framework is designed to be precautionary and to avoid the triggering of tipping points. That is the theory. In practice, this integration so far is still somewhat limited. So we are mainly implementing tipping point science into the framework by embedding it in the climate change boundary. One of the main reasons for that is that we, in this case, have fairly robust models and evidence where we can link the rise in global mean temperature or CO2 with the potential thresholds of the tipping elements in the Earth systems. But it's important to note that tipping points per se are not limited to climate. Yeah, I think it's easiest to understand if I give you an example. So you can see here that for the Amazon rainforest, the tipping threshold, tipping point, is estimated to be between 2 and 6 degrees of global temperature rise. But this range doesn't really capture actually the role of land system change, that is the role of deforestation, fire feedbacks, or regional rainfall decline. And just to basically show that, this is a time lapse from the Sentinel mission showing the evolution of the Amazon from 1984 until 2018. Maybe you didn't see like a lot of what was happening. So just basically, this is the 1984 state and this is the 2018 state. You can see a lot of deforestation, and as a fact is the Amazon has lost already about 20% of its forest cover, and the current cut down rate is approximately 1 football field every second. So really a lot. Now, this matters for our planetary boundary frame. I mean, it matters due to a lot of reasons, but for our framework, it matters because if we take into account this deforestation rate, then models show that the Amazon could already tip at already 1.5 to 2 degrees Celsius of warming. If we account for this, as I said, deforestation rate, or if it basically is combined with a 20 to 25 deforestation rate. So much sooner than the previously mentioned 3 to 5 degrees Celsius of warming. And just basically comparing that to the current situation, we are already at 1.2 degrees warming when we talk about the long-term warming. I know the last 1.5 years were even above 1.5 degrees. And 17, I think this number is fairly old. It's closer to 20% of deforestation. So showing that we actually need this information ideally on all tipping points. So not how they are only related to global warming, basically, and what could lead to a tipping there, but how are they related to changes in the land, in the freshwater cycle, in the nutrients and biodiversity, and so on. So, and we're trying to integrate that more and more into our framework. And this is just basically one example that shows how the planetary boundaries listed again here are highly interconnected. I don't really have the time to go into the details here, but if you want to learn more about that, please have a look at our report. I'm also going to link to that later. What I want to finish with is that the planetary boundary framework has been around for over 15 years, and it's being picked up now to evolve. We are doing that mainly in our team scientifically, but there's also are these initiatives to evolve it, let's say, ethically or justically, in the sense that here on the left, you see the original planetary boundary frameworks with the 9 planetary boundaries. And the Earth Commission actually used this concept and proposed an extension, which they call the safe and just operating space, which is shown here on the right. So they so far only managed to determine this for 5 of the 9 boundaries, which is important, or which adds to this biophysical limits of the planetary boundaries, a social justice layer, saying that, okay, we don't just want a healthy Earth overall, but also one where humans can really thrive and where it's being fair. And right now, for example, we would say with the climate change boundary, that's not really fair because already a lot of people are suffering from extreme events, and droughts and famine because of that, and so on. So this is really like adding this extra dimension, and is also considering actually basic consumption needs in terms of people need to have access to fresh water and so on. So an interesting thing, but also, of course, scientifically makes it way more complicated, because anytime basically humans come into the place and questions of justice and so on, it complicates the concept and you have to make more assumptions. And we already have some, enough open problems basically, or questions, to scientifically determine the natural limits. With that, I'm kind of basically done with my presentation. But I want to end, the following slides I added them because A, I want to end on a somewhat positive note, and B, I also wanted to give you some time to think about potential questions. So the next slides are showing how basically life or the planet could look like when we stay in the safe operating zone. And these were also created by the Earth Commission and Future Earth. And this is just basically examples of, okay, what measures would be needed to transform our life to stay within the planetary boundaries. Yeah, I'm just going to show that it's just a few slides giving examples for the different boundaries, and was also worked on basically in collaboration with different scientists to make sure that these are actual potential solutions. And with that, I'm done. And yeah, looking forward to some questions if there are some.
Thank you very much, Levke. It's a beautiful, first of all, yeah, super dense and beautiful presentation. Thank you for sharing all your insights in a condensed way. I'm sure people have questions in the audience. We're ready to take them. You can raise your hand or just unmute yourself or post it in the chat. I was wondering also, oh yeah, go ahead, Nicholas.
Please, you go ahead. Oh, good.
No, I just wanted to offer Levke what we discussed earlier, because she had a kind of a few thoughts about where she would like the discussion to go. So also feel free to, point that out, Levke.
Yeah, that would actually be great if I could start with that. So from this presentation, you can see that right now, as I said, it's mainly the climate change boundary that is informed by tipping point science. And the question is, of course, so anybody basically working on tipping points, whether we have other thresholds that are not just given in terms of a raise in global mean temperatures, but could also be related to if we basically interrupt the freshwater cycle, could that trigger some of our known tipping elements? I'm not quite pretty sure. I mean, I know the most obvious example really is the rainforest, and saying, okay, if we have land degradation or deforestation, this is definitely triggering the positive feedback loops. But maybe that is possible to determine for other tipping elements. So any basically knowledge on that would be highly appreciated, or insights on that.
Yeah, that's a very good question. Before we start with that, I have maybe I'm a little bit uncertain. So boundaries sounds like a sort of, you can draw a clear line, and we also saw a lot of very clear lines in your presentation. Now, at least, and with the sort of possible thresholds that we are concerned about, that they might exist in the climate system or in ecosystems in response to climatic changes or deforestation, land use changes. Our understanding currently is that the position is actually very uncertain. So first, sort of our knowledge on where these thresholds might be is sort of very limited. We have a lot of, I mean, that's where uncertainties come from, but then of course it also comes from sort of intrinsic variability and so on. To what extent does this whole concept of planetary boundaries really make sense if it's, if we're talking about ranges of a few degrees in the climate space, for example, and if that possibly, I could imagine, is very similar in the other in the other sections of planetary boundaries, we have this sort of very large uncertainty, both intrinsic and sort of just due to our lack of knowledge and understanding, and then lack of sort of measurability as well, I think. So does this really, do we really have the means to put clear boundaries on things?
Short answer, no. And this actually makes it scientifically quite frustrating to work with this framework. It's important to note that the framework is also being used as a mean of communication, basically, of drawing attention to different Earth system problems and crises. And I mean, on the one hand side, yes, you could say, okay, you can set a boundary using the precautionary principle and saying you always put it where the range of uncertainty starts. But as you say, Niklas, likely that range is going to be so large that the boundary is probably somewhere at a level that's impossible to stay below. And that actually shows that it is somewhat subjective in terms of, okay, what range of uncertainty or what level of uncertainty do I feel comfortable with, what I define as safe. And we are trying to change this to the process where it is 100% replicable, basically, of kind of saying, okay, informing it by model simulations and past variations. of the different planetary boundary variables, kind of see, okay, how do they evolve during the Holocene and so on. And then we can set a clear boundary saying, okay, now we are leaving this Holocene range of observed data. Again, also only somewhat, because also paleo data, of course, comes with ranges of uncertainty. So yeah, the short answer is no, we cannot really do that scientifically 100% sound, but of course we can do it in saying that, okay, we believe that the risk is fairly low below this point, and combined with the precautionary principle, then there are justifications for putting the boundaries at certain levels, but it is not 100% objective, to be honest.
Nicola, go ahead.
Right. Can you hear me?
Yes.
Yeah, thanks, Levke. So I have a question. This is more or less on the same level of Niklas. So it seems to me that there is a certain ambiguity, or perhaps it's just that I'm confused. I do not understand correctly. But it seems to me that there are something that you call threshold or boundary that have a kind of normative semantics. So this is something that you want to fix. You want to define clearly, although there are uncertainty, for instance, because you want to communicate a message, or because you want to raise attention on certain issues. This is something completely different from a threshold on a control parameter. For instance, what could be the critical concentration of CO2 in the atmosphere for a process that leads to, I don't know, sea level rise or abrupt change in ice sheet dynamics. So it seems to me that it would be worth giving different names to these different kinds of thresholds. So whatever, if you want a normative or recommendation character or something that you put in this framework, in order, for instance, to establish whether we are within or outside a certain safety region, and what are really, or what are then thresholds which are associated to well-defined processes that might be affected, as Niklas was saying, by very high uncertainty. And I think that the key for understanding this difference is the fact that what is a state in a subset of the climate system can be a control parameter for another subset of the climate system. And therefore, the same variable can play a multiple role, can play the role of a control parameter, but it also may play the role of, if you want, a state space, or for which then you want to define some kind of safety region. And I think that could help. So using different notions of thresholds for things which are, at least from within a system, control parameters and things that are states, could help bring perhaps a little bit more clarity in this situation, and perhaps also a little bit less frustration in a sense.
Yeah, that's a very good point. And I have to think about it actually some more. We are working towards that direction, but yeah, I'm just gonna, I guess, finish with that and saying that I'd love to basically email you about that, because it is a very good point. And as you said, it would reduce the frustration, because we do want this concept to be scientifically sound and informative. So changing the wording a little bit in the notion would make a lot of sense there. Thank you.
Thanks.
Ryan, please go ahead.
Yeah, thanks. That was a really nice talk, Levke. I really enjoyed it. Before I ask my question, which I think is also in the same vein, I'll just also comment that I also don't think it's necessarily bad that there's some subjectivity that goes into defining these boundaries. I mean, as long as it's clear, like how that reasoning is done and the logical process of how they're derived from that. But yeah, so my question is actually about uncertainty and how you kind of define it and how you think about it. So is uncertainty in this framework, as you think about it, primarily qualitative uncertainty or maybe like radical uncertainty, like things that we can't quantify? Or is it primarily quantitative? And to what extent do you think these uncertainties can be reduced by, for example, collecting more data, versus to what extent do you think maybe they're irreducible?
Very good question. So it's definitely qualitative uncertainties because we are hardly able to quantify any of them. There are probably a few of them that we could quantify, but the number and character, basically kind of uncertainties that we have so many and they're all mixed up that we basically just do a rough round. Okay, this is approximately an uncertainty. Some of them could be reduced by collecting more data, in the sense, of course, that we have on the one hand side the planetary boundary process, and then we have the control variable, which of course is also just a proxy for this process. So we already have some uncertainty there. Also, it would be a little bit difficult to quantify that, but we definitely can quantify the uncertainty. Well, not definitely, but we have a better chance in quantifying the uncertainty that we have because we have limited data. For example, when it comes to the ocean acidification, our problem is that we only really have good data for the surface, but we do, of course, know that all the subsurface processes play a role, and we can only approximate what is happening below the surface, but we do know that it plays a role. I think it makes sense, and that actually hasn't been done yet, that for the framework we make an overview of the different uncertainties, because when it comes to setting the boundary and determining whether or not we crossed it, of course, there's uncertainty in the current status of a process, but there's also uncertainty with the setting of the boundary. This is something we're just seeing with ocean acidification, where we said, okay, our threshold is basically 80% of the pre-industrial state. And suddenly we get to the point that due to new model simulations that model the Holocene state, they have a new estimate of what the pre-industrial state is. So our threshold suddenly jumps quite a lot, our boundary value, but not because the current status in any way changed, but only because our estimate of what happened in the Holocene state changed. So I would say we have a few chances of reducing some of the uncertainty, but right now there are too many to any way basically be able to really quantify them. But we haven't even been to the status where we sorted the different kind of uncertainty sources basically. So we would actually have to do that first and kind of see how they compare to each other and then go onward from there. But it's a good point, and definitely overall in the framework we haven't been thinking enough about uncertainties, kind of also using this precautionary principle as a way out a little bit, kind of saying, okay, as long as we have uncertainties with this threshold, we don't really have to determine it. We just have to be clear that we stay far below it. But that, of course, also really limits the applicability of the framework when it comes then, for example, to actually looking at regional policy recommendations and then listing thresholds. So yeah, it's also on our bucket list, basically, or to-do list.
Thank you.
We have Elisa and Joy.
Yes, hello. Thank you so much for the great presentation. I had a question also a bit about the applicability of the framework. So my partner and I, Joy, we have developed and regularly give a workshop on the Planetary Boundaries framework. And we often get questions on how the framework is currently used to guide policy and business practices. And we want to ask if you maybe can share some examples on how it's currently used and maybe how you envision it for the future.
So it's currently used, I guess, more as a helping guideline in terms of spreading awareness that it's not enough to just reduce CO2 emissions, but also basically you look at water consumptions and so on. There are a few partners that started to translate the framework, for example, for industry, businesses, and so on, but that really requires translations. For example, and we say in our original framework, we look at deviations in the freshwater cycle from the Holocene state and how that is regional applicable. no business could work with that, but they can work basically with, okay, the amount of fresh water they are consuming. And there are, doing this translation, you have to do a lot of assumptions, and that again introduces new uncertainties. We are slowly getting there. We've also seen that there are actually, for example, are now EU tenders out there to kind of say, hey, can you help us basically translate that for the EU? We have, of course, different ways of how we can, for example, say when we have a global threshold, we could say, okay, we distributed equally either by human population, GDP, and so on for the different countries and set thresholds for them. That is possible for a few boundaries, even not all of them. So I would say there are a lot of initiatives that try to do that right now. It is difficult. For the moment, honestly, if you want to apply it right now, I think it would be actually good to use framework that are all locally already in place when it comes to basically conserving nature, protecting nature, and just see how they topic-wise match up with the planetary boundaries. As I said, making it sure, yes, it is about basically reducing CO2 emissions, but it's also about reducing fertilizer use, about basically looking at the aerosol concentrations that we're putting into the atmosphere. How do we use our land? And if you basically just tick those topics, that would already be a good start. And we are working on really quantifying that for different regions at the moment, but that's going to take a couple of years at least.
Thank you for this practical guidance. Yeah, and we have a question in the chat. Wait, actually 3 questions, right? From Sophie. She says, your presentation links nicely with donut economics. My question is, do you weigh all 9 key processes equally? Say 2 processes have passed the boundary by the same amount, or can we determine which one to prioritize to bring back to the safe zone?
Yeah. So the answer is kind of no in both accounts. So A, we do not weigh them equally in the sense that we kind of say climate change and biodiversity loss, or basically the change in biosphere integrity, are probably the major ones because they are the ones that are the most highly interlinked with the other boundaries. But the truth is actually that we can't answer that question, yes, in terms of saying, okay, does this percentage basically of crossing the climate change boundary, and how far does it translate to how much percent of crossing of the freshwater boundary? We can't do that yet. We do know that it probably depends on the region where you are, so we can't even do that globally. We are working on that. What we can do is rather that if we look at different countermeasures, so what could we do to get back into a safe operating space? Then we could judge them basically, or rate them by, do they help all of the 9 boundaries? Do they only help 8 of them? Do they lead to a reduction of pressure in 2 of them, but increase the pressure in 3 of them? So we can do like this pro-con play and kind of say, okay, which measure moves which boundary in what direction? But otherwise, we're not there yet that we can do it. So a little bit frustrating. And as I said, also difficult because it does depend on the region. We are trying to at least kind of mark like hotspots of multiple boundary transgression. And as I said, kind of look at where do we have synergies when it comes to reducing pressures.
Right. And we have another question, which is about the Arctic sea ice, summer sea ice, why it's not included as identified as a tipping point, that the disappearance of the summer ice would have a knock-on effect on atmosphere and ocean circulation. Yeah, Victor says that this winter sea ice collapse is included in Mackay et al. 2022. Why not summer? Actually, we have David in the audience, so I think he took that question.
Yeah, if I can jump in, I'm the one who asked the question.
Right.
I appreciate McKay's answer here, and I understand the reasoning for it. I'm just a little bit fearful that it may have maybe brought away attention from the severe impacts of losing the Arctic summer sea ice because of this definition of there not really being a self-sustaining threshold, which leads to it disappearing, I guess.
I just really can say again, Nicola, I really appreciate your comment, and me and my team are going to look at that and probably do a follow-up email with you, because it really shows that scientifically the planetary boundary frameworks has to advance quite a lot, and it also has to become way more sound and more objective, and that is a great start doing that. So thanks for having me, and because I also learned a lot.